Hi my dear friends, welcome to our YouTube channel ADC Max. What are the boundary conditions for the one-dimensional wave equation dou squared y by dou t squared is equal to a squared into dou squared y by dou x squared? So, in the one-dimensional wave equation, the string is fixed at 2 points, that is between x equal to 0 and x equal to l. So it is fixed. Fixed means there is no vibration, there is no displacement at all at these 2 points. Clear? And we may allow the string to vibrate transversely, strictly in the xy plane, so that each and every particle of the string moves strictly vertically. So that we have to find the displacement of the string during the subsequent motion. So that is the requirement. Now, this case, when the string was vibrated, we can divide it into two special cases, depends on their velocity. Suppose initially the velocity is 0, what happened? Suppose initially the velocity is given, that is non-zero, what happens? So there are two different cases. So there are 4 boundary conditions for the one-dimensional wave equation. First boundary condition for the left extreme point, at this point it is fixed, so there is no displacement. So at x equal to 0, for any time t, there is no displacement. Got it? Second boundary condition for the right extreme, at x is equal to L. Once again, at this point, at this juncture, it is fixed, so no displacement taken. So at x is equal to L, the displacement is once again 0 for any time t. Now, there are 2 boundary conditions for x, one for x equal to 0, one for x equal to L. The other 2 boundary conditions for t equal to 0, that is initially time t equal to 0. Here, the velocity is 0 and initially that comes as the third boundary condition, because the 0 boundary conditions first listed out, then the non-zero boundary conditions listed at the last. So once the velocity is 0, so the third boundary condition is the rate of change of displacement with respect to time t is velocity, isn't it? Initially time t equal to 0 is 0. So velocity initially time t equal to 0 is 0 in between 0 and L, because at x equal to 0 is the first boundary condition, at x equal to L is the second boundary condition, isn't it? So in between 0 to L, at the time t equal to 0, initially the velocity 0 is the third boundary condition. And what is the velocity 0? The displacement at initially is given. So fourth boundary condition is initial displacement function y of x comma t equal to 0 is a function of x is in between 0 and L. So these are the boundary conditions under the case of 0 initial velocity. So what about the non-zero initial velocities? Even though the velocity is non-zero, the first 2 conditions are same, isn't it? At x equal to 0, no displacement. At x equal to L, no displacement. So once the string may allow by giving some initial velocity, thus each and every points of the string, the displacement function is 0 at initially. So once the velocity is given, then the initial displacement is 0. So the third boundary condition is initial t equal to 0, displacement is 0. So fourth one is velocity is non-zero. So dou y by dou t at the time t equal to 0 is a function of x, because t equal to 0. That is the fourth boundary condition. So in both the cases, first 2 conditions are retained. X equal to 0, no displacement, x equal to L, no displacement, because of these 2 points are fixed. the velocity is 0, third condition is velocity 0, then displacement is non-zero. Right? So always the non-zero boundary condition listed out in the last, the final condition. And once the velocity is non-zero, then the fourth condition becomes non-zero initial velocity, third one becomes displacement function as 0. So when t equal to 0, displacement is 0. When t equal to 0, velocity is non-zero. Suppose the velocity is 0, third one is velocity 0. Displacement is non-zero. So anyhow, first two conditions are still same, no changes in the first two conditions. So these are the boundary conditions. Now my question is, what are the use of these boundary conditions? What is the use? As I already told you that when we solve the one-dimensional wave equation by using the method of separation at variable technique, we may found three possible solutions. Among the three, one is the periodic function, that is a cos px plus b sin px. So two constants for x and two for the t, that is c cos pat plus d sin pat. So let us apply the boundary conditions one by one in this correct solution. We may able to determine the constant value. When we apply the first boundary condition in the correct solution, you may get a equal to 0. We may get a equal to 0. When we apply the second boundary condition, we get p is equal to n pi by l. P is equal to n pi by l. When we use the third boundary condition, I am getting that d equal to 0 under the initial velocity 0 case. But at the same time, the non-zero velocity means the condition is displacement. At this time, we get c equal to 0. So see the difference. First two conditions, no changes. Then third condition is changed. So that's why we get d equal to 0. Here we get c equal to 0. Got it? Right, sir? So this is the idea in the boundary conditions for the zero initial velocity and the non-zero initial velocity for the one-dimensional wave equation. Even though there is a huge difference in the final solution, for the zero initial velocity, the most general solution, the final answer is in the zero initial velocity. Y be the function of x comma t, we get it is sigma n is equal to 1 to infinity capital Bn sin n pi x pi L into cos n pi at by L. So this is the required displacement function under the zero initial velocity. One term x for 1 for t is trigonometric term, is also trigonometric sine and cos. But in the case of non-zero initial velocity, the most general solution for the non-zero initial velocity is y of x comma t is equal to sigma n is equal to 1 to infinity Cn sin n pi x by L into sin n pi at by L. See that both are trigonometric functions, both are same sine function. Why? Let us see that a0 p equal n pi by L c0. So that's why we get sine. Because as you see, what is the correct solution? The correct solution is y of x comma t is equal to a cos px plus b sin px into c cos pat plus d sin pat. So this is my correct solution. Let us apply the conditions one by one. What I am getting that? When I use the first boundary condition, a equal to 0. So this becomes 0. When I use the second one, we get p equal to n pi by L, p equal to n pi by L, p equal to n pi by L. When I use the third boundary condition under the zero velocity, d equal to 0. Is right? So that's why we get sin n pi x by L cos n pi at by L. Sin n pi x by L cos n pi at by L. I combine both b and c as bn. But under the non-zero velocity, what happened? Once again, the first condition a equal to 0, second one p equal to n pi by L. But under the non-zero initial velocity, the initial displacement is 0. Once the initial displacement is 0, we get c equal to 0. So this time c becomes 0. So a0, c0. What's the balance? The balance is b sin px and d sin pet. If I combine b and d as cn, if I combine b and d as the arbitrary constant cn, then replace p by n pi by l, we get sin n pi x by l, sin n pi at by l. So this is the huge difference in the most general solution for the zero initial velocity as well as non-zero initial velocity. Thank you for watching our YouTube channel. This is your ADC. This is your YouTube channel, ADC Max. I am signing off. Thank you. Take care. Bye.